The liar paradox. You meet a stranger on the road. He looks you in the eye and says, "Everything I say is a lie." You pause. If what he's saying is true, then he must be lying. But if he's lying, then what he just said must be false, which means he's actually telling the truth. But if he's telling the truth, then your brain stutters, trapped in an infinite loop. Logic itself begins to collapse. Welcome to the liar paradox, also known as the Epimenides paradox, a riddle so deceptively simple that it shatters our understanding of truth, logic, and meaning itself. Once you step into this paradox, you may never see reality the same way again. Before we go on, kindly use this opportunity to subscribe to my YouTube channel and fall asleep as you listen to educational contents. The liar paradox is one of the oldest and most mind-bending puzzles in philosophy. It dates back to Epimenides, a philosopher from ancient Crete, who famously declared, "All Cretans are liars." But here's the problem. Epimenides himself was a Cretan. If he was telling the truth, then Cretans really are liars, which means he must be lying. But if he's lying, then Cretans are actually honest, which means he's telling the truth. And suddenly, truth collapses in on itself. Now, let's simplify this paradox to its purest form. This statement is false. If the statement is true, then it must be false. But if it's false, then it must be true. The sentence keeps flipping back and forth endlessly, like a snake eating its own tail. This isn't just wordplay. This paradox exposes a deep flaw in the way we define truth itself. If we can't determine whether a simple statement is true or false, how can we ever be sure of anything? Our entire understanding of the world is built on the idea that statements are either true or false. When someone says, "The sky is blue," we assume that statement has a definite truth value. But the liar paradox breaks the system. It shows that some statements can't be neatly classified as true or false. This is deeply disturbing because our entire logical framework depends on clear distinctions. If we can't even determine the truth of a single sentence, how much of our knowledge is built on shaky ground? Philosophers and logicians have spent centuries trying to fix the liar paradox. Here are some of the most famous attempts. Rejecting self-reference. Some argue that the problem arises because the statement refers to itself. If we simply ban self-referential statements, the paradox disappears. Three-valued logic. Instead of just true or false, some propose a third option. Undefined. The liar paradox isn't true or false. It's just meaningless. Context-based solutions. Some say truth depends on context. Maybe this statement is false doesn't create a paradox. It just lacks a stable meaning. But no solution fully satisfies everyone. The paradox remains unsolved, lurking at the edges of logic, reminding us that even the simplest truths can be deceptive. Final thought. What if everything is a lie? The liar paradox teaches us something profound. Truth is more fragile than we think. We like to believe that the world is made of clear, definable truths, that statements either describe reality accurately or they don't. But the liar paradox whispers a darker possibility. What if truth itself is an illusion? Maybe reality isn't built from solid facts, but from an ever-shifting web of meanings, contradictions, and paradoxes that can never fully be resolved. So the next time you hear someone claim, "This is the absolute truth," pause for a moment. Consider the possibility that the truth is not as simple as it seems. And remember, sometimes the deepest mysteries of existence hide inside the simplest of sentences. This statement is false. Now, try to sleep with that thought in your mind. The Barber Paradox. In a quiet town, there's a barber. He's well-known, precise, and follows one simple rule. He shaves everyone who does not shave themselves. That's it. That's the rule. One day, someone asks a seemingly harmless question. Does the barber shave himself? And in that instant, reality collapses. If the barber shaves himself, he's breaking his own rule, because he only shaves people who don't shave themselves. But if he doesn't shave himself, then according to his rule, he must shave himself. It's a loop with no escape, a contradiction that can't be resolved, a paradox so simple, yet so devastating, that it exposes deep flaws in the way we think about logic itself. Welcome to the Barber Paradox, a problem so deceptive it haunted some of the greatest minds in history and still refuses to be solved. At first glance, the Barber Paradox seems like a quirky word puzzle, like something you might hear at a dinner party. But beneath the surface, it reveals something far more unsettling. This paradox, introduced by Bertrand Russell, isn't just about barbers. It's about self-reference and the fundamental cracks in our logical systems. It's part of the same discovery that led to Russell's paradox, a problem that nearly broke mathematics itself. Because if a simple rule like the barber shaves everyone who doesn't shave themselves can create a contradiction, then how many other contradictions are hiding inside systems we believe to be perfect? This paradox shows that certain rules can't logically exist. The very act of defining them creates a contradiction. It also raises deeper questions. Can we ever truly define a perfect logical system? Are there statements in the universe that simply can't be classified as true or false? What happens when reality itself breaks down? This paradox wasn't just a fun puzzle for Russell. It was a warning, a sign that even in mathematics, where everything is supposed to be precise and provable, there are unavoidable paradoxes that shake the entire foundation of logic. You might be wondering, okay, but does this paradox actually matter outside of philosophy? Yes, more than you might think. Keycap won artificial intelligence and programming. Imagine an AI that is programmed with strict rules. Like our barber, what happens when it encounters a self-referential contradiction? It crashes. This is why paradoxes like this are crucial in computer science, to prevent AI systems from falling into infinite loops. Keycap 2 mathematics and set theory. This paradox led to a much larger discovery, that some systems of logic are fundamentally flawed if they allow self-reference. Modern math had to be rewritten to avoid contradictions like this. Keycap 3 real-world logic and ethics. Imagine a law that states, all rules must be followed, except when they contradict themselves. Now, what happens when a rule both must and must not be followed? Paradoxes like this shape how we write laws, create systems, and define logic itself. Is there a solution? So, can the Barber Paradox be solved? The answer is no. It's an impossible scenario. The paradox happens because the barber cannot logically exist. His rule breaks itself the moment it's created. One way to fix it is simply to reject the premise. The barber cannot shave exactly the people who don't shave themselves. The rule contradicts itself, meaning the situation is logically impossible. But that's the terrifying part. If logic itself can create contradictions, then how many other paradoxes are lurking beneath the surface of reality? Final thought. The Barber Paradox is more than just a mind game. It's a reminder that even the most logical rules can fail. We like to believe that the universe operates on clear, rational principles, that rules define how everything works. But what if, deep down, the universe contains paradoxes we can never resolve? What if some questions, no matter how simple, simply have no answer? So, the next time someone presents you with a rule that seems airtight, remember the barber and ask yourself, does the barber shave himself? Or does logic just collapse when no one is looking? The Grandfather Paradox. You step into a time machine, set the dial to the past, and press the button. In an instant, you're standing decades before your own birth, face to face with a young man, your grandfather. For a moment, curiosity takes over. But then, a dark thought creeps in. What if you stopped him from meeting your grandmother? It would be simple, a misplaced letter, a minor accident, or something far worse. But here's the terrifying question. If your grandfather never has children, then your parent is never born. And if your parent is never born, you were never born, which means you never traveled back in time, which means your grandfather did meet your grandmother, which means you were born. And just like that, you've created an impossible loop, a paradox so mind-bending that it threatens to break the very fabric of time itself. Welcome to the Grandfather Paradox, the ultimate nightmare of time travel. And once you step into this paradox, there may be no way out. The Grandfather Paradox is one of the most famous and terrifying dilemmas in time travel theory. At its core, it challenges our understanding of cause and effect, the idea that the past creates the future in a logical sequence. But what happens when the future interferes with the past? This paradox suggests that if time travel to the past were possible, the very act of changing something, no matter how small, could unravel reality itself. The key problem? Self-contradiction. The paradox creates a loop where your own existence is both necessary and impossible at the same time. It's a logical impossibility, and yet here we are still wondering if time travel could one day be real. Scientists and philosophers have debated possible solutions to the Grandfather Paradox, but none of them are entirely satisfying. Here are the main theories. The Novikov self-consistency principle. The universe won't let you. Russian physicist Igor Novikov proposed that time travel might be possible, but the universe would always prevent paradoxes. If you went back in time and tried to stop your grandfather from meeting your grandmother, something would always interfere. Maybe you trip at the last second, or your gun jams if you try something drastic. In this view, time is like a film strip. You can move through it, but you can't change what's already been recorded. Parallel universes, every choice creates a new reality. Some scientists believe that instead of creating a paradox, changing the past would simply create a new timeline. In this version, when you prevent your grandfather from meeting your grandmother, you don't erase yourself. You just shift into an alternate universe where you never existed. The original timeline remains intact, but you're now trapped in a different one, where you can never return to your original reality. The timeline correction theory. Time heals itself. Another idea is that small changes to the past will always get corrected over time. Maybe you stop your grandfather from meeting your grandmother at the dance, but later they bump into each other at the grocery store and fall in love anyway. In this view, the past is flexible, but major paradoxes will always fix themselves. The Grandfather Paradox is one of the biggest reasons why many scientists believe time travel to the past is impossible. If time travel ever existed, then paradoxes like this could rip reality apart. Yet, physics doesn't completely rule it out. Einstein's theory of relativity allows for time dilation, meaning time can slow down or speed up depending on how fast you move. Wormholes, theoretical shortcuts through space-time, might allow travel to the past, but they come with their own paradoxes. Quantum physics suggests that reality might not be as fixed as we think, leaving the door open for strange possibilities. So, If time travel is possible, would you risk using it? Would you go back in time to fix your past, knowing that one wrong move could erase you from existence? Or worse, what if someone else already has? One thing is certain. If the grandfather paradox proves anything, it's that time is not as simple as we think. And if time travel ever becomes real, we may not live to understand the consequences. The Bootstrap Paradox. Imagine discovering a book filled with knowledge centuries ahead of its time. You memorize every word, then travel back in time and give it to a young writer, who then publishes it, making it famous. But wait, where did the book actually come from? This is the Bootstrap Paradox, a mind-bending riddle where an object, idea, or person exists without ever having been created. A violin, a mathematical equation, or even your own existence. Looping through time with no clear beginning. If something has no origin, does it really exist at all? Or is reality just a tangled web of infinite loops? Let's unravel the paradox. The Bootstrap Paradox is one of the strangest and most unsettling puzzles in time travel. It's a causal loop where something is pulled into existence without any clear origin. Think about it this way. Imagine a scientist from the future builds a time machine. Before they make any groundbreaking discoveries, they travel back in time and give their younger self a notebook filled with all the equations they need. Their younger self then studies the notes, becoming the genius who later writes them down in the same notebook. So, where did the information actually come from? Who wrote it first? The knowledge seems to exist in a perfect loop with no real starting point. It was never invented, just passed through time forever. And that's where the paradox emerges. The term Bootstrap Paradox comes from the old expression, pulling yourself up by your bootstraps, meaning to do something impossible, like lifting yourself into the air by tugging on your own shoes. This paradox is a direct challenge to causality, the fundamental principle that every effect must have a cause. In a Bootstrap Paradox, the effect is its own cause. The object or information exists in an endless loop with no clear point of origin. This paradox has appeared in many thought experiments, science fiction stories, and even real scientific discussions. Here are some famous examples. Beethoven's Symphony, a musical mystery. A time traveler, knowing Beethoven's music, goes back in time and teaches it to a young Beethoven. But if Beethoven only learned the music from the traveler, who originally composed it, the time-traveling violin, a musician finds an old, beautifully crafted violin and takes it back in time to have it copied by a master luthier. The copied violin is then passed down through history, eventually becoming the very same violin the musician originally found. But who built the first one? Doctor Who's watch. In an episode of Doctor Who, the Doctor receives a watch from someone, then later goes back in time and gives it to the same person. The watch exists in an infinite time loop with no clear origin. These examples all share a common theme, something existing without ever being created. It's a paradox that not only challenges our understanding of time, but also forces us to rethink the nature of reality itself. Why is the Bootstrap Paradox a problem for physics? At first glance, the Bootstrap Paradox seems like just a fun thought experiment, but it raises serious questions in physics, especially when it comes to time travel and the laws of the universe. The law of conservation of energy. Energy and matter cannot be created or destroyed, only transformed. But if an object appears out of nowhere due to a time loop, where does its energy come from? Causal consistency. The universe runs on cause and effect. But in a Bootstrap Paradox, the effect creates the cause, breaking the natural order of time. The multiverse theory. Some scientists suggest that paradoxes like this might be avoided if time travel creates alternate realities instead of looping within a single timeline. If the Bootstrap Paradox were possible in reality, it could mean that some things in our universe might not have an origin at all. They just exist because time allows them to. Can the Bootstrap Paradox be solved? Philosophers and physicists have debated whether the Bootstrap Paradox is truly a problem or just a misunderstanding of time. Some potential explanations include predestination. The universe is already written. Some argue that the timeline is already set, and paradoxes like this are simply part of how reality functions. If Beethoven's symphonies were always meant to exist, then they exist regardless of how they were introduced into history. The information has no true origin. Some physicists propose that time is a self-contained structure where information can loop infinitely without needing an external origin. It's just there, a self-sustaining loop. Time travel is impossible. The simplest answer? Maybe time travel into the past is impossible. If time paradoxes break the universe, then nature might have built in safeguards, preventing time loops from ever happening. Final thought. The Bootstrap Paradox challenges our understanding of causality, time, and even existence itself. If information, objects, or even people can exist without an origin, what does that say about the nature of reality? What if something in our world is the result of a Bootstrap Paradox? A scientific breakthrough, a famous invention, or even a work of art, existing without an original creator? Maybe time isn't a straight line. Maybe reality is filled with loops, with things that exist simply because they always have. And if that's true, then perhaps the biggest question isn't where things come from, but whether an origin even matters at all. Now, think about this. Did you find this video, or did it find you? Newcomb's Paradox. You walk into a room, and on a table in front of you, there are two boxes. One is transparent, and inside, you can clearly see $1,000. The other is opaque, and you have no idea what's inside. Except for one thing. Someone has told you that it either contains $1 million or nothing at all. You now have a choice. Take only the opaque box. Take both the opaque box and the transparent box with the $1,000. It seems simple, right? Just take both and walk away with at least $1,000. But here's where things get weird. Before you enter the room, a highly advanced predictor, a being, a machine, an alien, or even an all-knowing oracle, has already predicted what you'll choose. And this predictor is almost never wrong. If it predicted you would take both boxes, it left the opaque box empty. If it predicted you would take only the opaque box, it placed $1 million inside. So now, you stand in front of the boxes, but the choice has already been made for you in the past. The $1 million is either there or it isn't, based on what the predictor foresaw. So, what do? At first glance, there seem to be two logical ways to approach this puzzle, but they completely contradict each other. Argument 1. Take both boxes. The logical thinker's choice. This is called the dominance argument. It says, the money in the opaque box has already been placed, or not, before you even walked in. Whether you take one box or both won't change what's inside the opaque box. So why not take both and guarantee at least $1,000? Simple, right? But here's the problem. Argument 2. Take only the opaque box, the trusted predictor choice. This is called the expected utility argument. It says, if the predictor is almost never wrong, then it already knew what you choose. If you take both boxes, the opaque box is empty, and you get only $1,000. If you take only the opaque box, then the predictor must have foreseen that decision and placed $1 million inside. So if you want the most money, you should take only one box. Both arguments seem completely logical, and yet they directly contradict each other. So which one is right? Newcomb's paradox isn't just about money. It's about the deepest questions of free will, determinism, and decision-making. If the predictor is truly infallible, then your choice isn't really a choice at all. It was decided before you even thought about it. This suggests that free will is just an illusion. We are all just acting out a script that has already been written. On the other hand, if you believe in true free will, then you should be able to defy the predictor's expectations and make any decision you want. But if that were the case, then the predictor wouldn't be infallible, and yet it always seems to be right. This paradox shakes the foundations of what we think we know about reality. Newcomb's paradox has been used to challenge ideas in quantum mechanics. Does reality exist independently, or is it shaped by our choices? Artificial intelligence. Could a superintelligent AI predict our behavior perfectly? Philosophy of mind. Do we have free will, or is everything predetermined? Game theory. How do we make decisions when faced with uncertainty? This paradox isn't just a puzzle. It's a question about the very nature of existence. So, what would you choose? Would you trust a predictor and take only the opaque box, risking getting nothing but potentially walking away with $1 million? Or would you take both boxes, playing it safe, but possibly proving the predictor right and losing out on the million? The choice is yours, or is it? Think carefully, because if someone or something is watching, your decision might have already been made. And that's the real paradox. The Sorites Paradox. Imagine you're standing in front of a giant heap of sand, thousands, maybe millions, of grains stacked together, clearly forming a heap. Now, what happens if you remove just one grain? Surely, it's still a heap, right? Okay, let's remove another one, and another, and another. At what exact point does this heap stop being a heap? If a single grain of sand isn't a heap, and removing one grain never seems to make a difference, then can we ever really say a heap even existed in the first place? This is the Sorites Paradox, also known as the paradox of the heap, and it reveals a deep flaw in the way we define things in everyday life. The Sorites Paradox exposes a problem with vague concepts, words that don't have clear boundaries. We can all agree that a single grain of sand isn't a heap. But as we add more and more grains, at what point do we cross the invisible line where it becomes a heap? Is 2 grains a heap? Probably not. How about 10? 100? 1,000? If you think 1,000 grains make a heap, what about 999? There seems to be no precise moment when a non-heap turns into a heap. And yet, we use the word heap all the time without confusion. So, what's going on here? The real problem at the heart of this paradox isn't about sand. It's about the way language and logic interact. We rely on fuzzy concepts every day. Consider these. Baldness. If you lose one hair, you're not bald. If you lose another, you're still not bald. But at some point, you are. When exactly? Tallness. If a person is 5 feet 11 inches, are they tall? What about 6 feet 0 inches? 6 feet 1 inch? Wealth. If you save $1 every day, at what point do you become rich? Our language is full of concepts that work without clear boundaries. The Sorites Paradox exposes how those concepts break down when pushed to the extreme. Can we fix the paradox? Philosophers and logicians have debated solutions to this paradox for centuries. Here are some of the most famous ideas. 1. Drawing an arbitrary line. Some argue that we should simply pick a number and say, this is the cutoff. For example, we could declare that 1,000 grains make a heap and 999 do not. But this feels unnatural. Why should one grain suddenly make all the difference? 2. Fuzzy logic, the gray area approach. Instead of thinking in absolute terms, heap or no heap, fuzzy logic suggests we think in degrees. A single grain of sand is 0% heap. A small pile might be 30% heap. A massive pile is 100% heap. This allows for a smoother transition rather than an all-or-nothing approach. 3. Rejecting the question, the it doesn't matter approach. Some philosophers argue that the paradox only exists because we assume words must have precise boundaries. In reality, language is flexible. We don't need a strict definition of heap to understand what it means in context. The problem only arises when we force precision onto a vague concept. The Sorites Paradox might seem like a fun little puzzle, but its implications go far beyond sand. In law and ethics, when does a group of people become a crowd? When does an action become unethical? In AI and computers, machines struggle with vague concepts because they rely on strict logic. In medicine, at what point does someone go from healthy to sick? In identity, if you gradually replace every part of an object or even a person, when does it stop being what it was? The paradox forces us to confront the limits of language and reasoning, showing that many of our everyday ideas aren't as solid as they seem. So, what do you think? If a heap isn't defined by a specific number of grains, then what is it defined by? And if vague words like heap, tall, or rich don't have clear definitions, then how much of what we believe is actually just a useful illusion? Maybe a heap is just a state of mind. Or maybe it was never a heap at all. Zeno's dichotomy. You take a step forward, just one step. But what if I told you that you'll never actually reach your destination? That no matter how hard you try, no matter how many steps you take, you will always have an infinite number of steps left to go? It sounds absurd, doesn't it? After all, you walk every day without a second thought. But what if I told you that, mathematically, motion itself should be impossible? That every time you try to move, you are trapped in an endless loop of fractions, an infinite sequence of tasks that must be completed before you can even cross the smallest of distances? This is not a trick. It's not science fiction. It's an ancient paradox, one that has baffled philosophers and mathematicians for over 2,000 years. A paradox that suggests movement, the very thing that allows you to exist, to breathe, to live, should not be possible at all. Imagine you are standing at the beginning of a journey. Ahead of you lies a destination. Perhaps a cozy chair across the room, a quiet park bench in the distance, or even the farthest reaches of the universe. You take a step forward, but before you can reach your goal, something curious happens. You must first reach the halfway point. Then, before reaching the end, you must travel half of the remaining distance. And again, half of that. And so on endlessly. This is Zeno's Dichotomy Paradox. And once you step inside its logic, you may never see motion the same way again. At first glance, it seems to suggest something quite absurd, that motion itself should be impossible. If we must complete an infinite number of steps to reach even the simplest destination, how could we ever get anywhere at all? Yet, in the world we know, people move, rivers flow, and planets orbit. There is no hesitation, no infinite delay. So where does this paradox come from, and why does it feel so unsettling? The paradox was first proposed by the ancient Greek philosopher Zeno of Elea, who crafted it as an argument against the idea that space and time are continuous and infinitely divisible. He reasoned that if space can be divided infinitely, then motion must require an infinite number of steps to complete, even over the shortest distances. But if we need to finish an infinite number of tasks just to move an inch, how can motion ever begin? Of course, we know that in reality, movement happens smoothly. So what's the solution? Mathematicians eventually resolved this paradox through the concept of converging infinite series. While it's true that there are infinitely many steps in the process Zeno describes, each step takes less and less time to complete. When we add up all these infinitely small fractions of time, they sum to a finite number. The journey does not take forever. It just feels paradoxical when we think of it in terms of infinite steps. This is where calculus and the idea of limits come in. Developed centuries later by Newton and Leibniz, calculus allows us to understand how infinite sequences can add up to a finite result. In essence, our everyday experience of motion aligns with mathematical reality, even if Zeno's framing of the problem seems to argue otherwise. But the paradox still leaves us with something to ponder. What does it mean to divide reality into infinitely small pieces? Is motion a continuous, flowing process, or do we move in discrete steps too small to perceive? And if the universe itself is made up of finite, indivisible units, perhaps tiny quantum building blocks, does that mean Zeno was onto something all along? Consider the nature of time itself. Much like space, we perceive time as a continuous flow, but some theories in quantum mechanics suggest that time, like space, might have a smallest possible unit, a quantum of time. If this is true, then motion may not be infinitely divisible at all, but instead a series of tiny jumps so minuscule that we don't notice them. Could it be that Zeno's paradox hints at the fundamental structure of the universe, something ancient philosophers could not yet articulate but modern science is just beginning to explore? Now, think of a simple task: reaching for a book on a shelf, walking to a door, or even stretching your hand out to touch someone else's. Each of these actions, when viewed through the lens of Zeno's paradox, seems impossible, and yet you complete them with ease. This raises another intriguing question. How do we reconcile our intuitive experience of movement with the logical, yet puzzling, implications of the paradox? One way to look at it is through the practical lens of physics. When an object moves, it does not stop to calculate infinite subdivisions of distance. Instead, movement is governed by forces, inertia, and acceleration, concepts that allow motion to proceed without hesitation. The paradox arises only when we attempt to analyze motion through pure logic, rather than through physical reality. Another perspective comes from cognitive science. Our perception of movement is shaped by our brain's ability to process visual and spatial information. We don't experience motion as a series of discrete steps, but as a fluid, continuous phenomenon. Could it be that our brains have evolved to bypass these paradoxes, allowing us to interact with the world without being trapped by infinite subdivisions? There is also a poetic beauty in Zeno's paradox. It reminds us that our understanding of reality is limited by the way we frame questions. By breaking motion into an infinite series of steps, we create a problem that does not exist in the real world. But in doing so, we expose deep truths about the nature of infinity, mathematics, and perception. And so, as you drift into relaxation, consider this. Motion, time, and space are not as simple as they seem. The next time you take a step, feel the weight of an ancient paradox beneath your feet. Even in the smallest of movements, an infinity unfolds, and yet, somehow, you still arrive. Perhaps, in a way, life itself is a paradox, a journey of infinite moments, all leading to something greater. a path we take step by step, always moving forward, even when the destination remains just beyond our reach. Now, let your mind wander further. Consider how this paradox applies beyond movement itself. Could it reflect the way we strive for knowledge, always reaching for the next bit of understanding, only to find that there is always another question, another discovery, another horizon? Could it be that progress, like motion, is an infinite pursuit? Think of the moments that make up your life. Each one leads to the next, forming an unbroken chain of experiences. But if we apply Zeno's reasoning, is there ever a final, completed moment? Or is every instant just another step toward an unreachable conclusion? And yet, despite all this, you continue. You move, you grow, you change. The infinite does not hold you back. It carries you forward. Close your eyes and feel the motion within you, the beating of your heart, the rhythm of your breath, the steady pulse of time itself. All of it, an infinite unfolding, moment by moment, step by step. And as you drift deeper into thought, remember, even in the paradox, there is beauty. Even in infinity, there is motion. And even in the endless journey, there is rest. Achilles and the Tortoise. Picture this, a massive stadium packed with roaring spectators. The sky is bright, the ground is hot, and at the starting line, two racers stand ready. On one side, Achilles, the mightiest warrior of ancient Greece, swift as the wind, undefeated in battle. His muscles are tense, his eyes locked forward. Victory is certain. On the other side, a tortoise, slow, steady, almost laughable in comparison. The crowd chuckles. How could this possibly be a fair race? But the tortoise has a small advantage, a head start. Let's say 10 meters. The signal sounds. Achilles takes off. Within seconds, he reaches the spot where the tortoise was. But the tortoise has inched forward. Achilles surges ahead again, closing the gap, but the tortoise has moved again. No matter how fast Achilles runs, the tortoise always stays ahead. It sounds absurd. It feels wrong. And yet, the logic suggests something shocking. Achilles can never actually pass the tortoise. This is Zeno's paradox of Achilles and the tortoise, a riddle so deceptively simple, yet so disturbingly profound that it has puzzled philosophers and mathematicians for over 2,000 years. And once you step into its logic, you may never look at motion or reality the same way again. At first, you might think this is nonsense. Of course, Achilles overtakes the tortoise. I've seen people outrun slower runners countless times. But the paradox doesn't care about intuition. It works like this. Achilles starts at point A, and the tortoise is at point B. Achilles reaches point B, but by then, the tortoise has moved to point C. Achilles reaches point C, but the tortoise has moved to point D. This continues forever. Every time Achilles arrives where the tortoise was, the tortoise has moved just a little farther. Even though the gaps are shrinking, Achilles must complete an infinite number of steps to catch up. And if he must complete an infinite number of tasks, how can he ever overtake the tortoise? This is the trap. Zeno's paradox suggests that motion itself is an illusion, that if space and time are infinitely divisible, then reaching any destination should be impossible. And yet, Achilles does pass the tortoise. So what's going on? We know from experience that Achilles wins. So why does the paradox feel so convincing? The problem isn't Achilles' speed. It's how we think about infinity. 1. Infinite steps, finite time. Yes, Achilles must complete an infinite sequence of steps. But that doesn't mean he needs an infinite amount of time. Small blue diamond, the distances Achilles covers gets smaller and smaller each time. Small blue diamond, the time required for each step shrinks as well. Small blue diamond, when we add up this infinite series, the total time is finite. Achilles does reach and pass the tortoise. This is where calculus comes to the rescue. Even though this sequence contains an infinite number of terms, the sum converges to a finite limit. Achilles completes all the steps in a finite time and easily passes the tortoise. The paradox tricks us because our brains aren't wired to handle infinity intuitively. We assume infinite steps mean infinite time, but that's not always the case. Zeno's paradox isn't just a quirky thought experiment. It forces us to question fundamental assumptions about space, time, and reality. 1. Is motion an illusion? If every movement can be broken into an infinite number of parts, do we ever truly move? Or do we just experience the illusion of movement? Some philosophers suggest that motion is not continuous, that it happens in tiny, indivisible jumps like frames in a film. Could reality be operating on a hidden frame rate we can't perceive? 2. Is space continuous or made of smallest pieces? Zeno's paradox relies on the assumption that space is infinitely divisible. But what if it's not? Modern physics suggests that at the smallest scales, on the level of quantum mechanics, space and time may be quantized. That is, there could be a smallest possible unit of distance, beyond which division is impossible. If true, this would mean Achilles isn't completing an infinite series of steps, because at some level, space itself stops dividing. 3. How does infinity affect real-world science? Infinity isn't just a philosophical headache. It changes how we think about physics, technology, and even artificial intelligence. Small blue diamond calculus, which resolves this paradox, is the foundation of physics, engineering, and AI. Without it, we couldn't send rockets to space, predict climate change, or train neural networks. Small blue diamond quantum mechanics may offer the real solution to the paradox. If time and space aren't infinitely divisible, then Zeno's paradox never truly applies to reality. Final thought. At its core, the paradox of Achilles and the tortoise isn't just about running. It's about how we understand reality itself. Zeno's logic suggests Achilles shouldn't win, but mathematics, physics, and experience prove otherwise. So, what does this mean for you? Maybe the lesson isn't just about motion. Maybe it's about progress. Think about your own life. Every goal you set, every dream you chase. It can feel like you're always moving towards something but never quite arriving. Like Achilles, you take step after step, but the finish line keeps shifting. The goal always seems just out of reach. But just because the journey seems infinite doesn't mean you aren't getting there. Like Achilles, you do overcome the impossible, step by step, moment by moment. And just like Achilles, one day, you'll look back and realize the tortoise is far behind you. So keep running. The paradox may never fully disappear, but neither will your ability to win. Russell's Paradox. Imagine a massive library, one that holds every catalog in the world. Inside, there are two types of catalogs. Catalogs that list themselves like a catalog of all science books, which includes itself because it's a science book. Catalogs that do not list themselves, like a catalog of all fiction books, which doesn't include itself because it's not a fiction book. One day, a librarian has an idea. I will create a new catalog that lists every catalog that does not list itself. At first, this seems fine, but then the librarian asks, should this new catalog include itself? And that's when the paradox explodes. If the new catalog lists itself, then it shouldn't be in the catalog, because it only includes catalogs that don't list themselves. But if it doesn't list itself, then by definition, it should be in the catalog. It's a contradiction. No matter what, the library cannot exist in a logically consistent way. This puzzle isn't just an intellectual curiosity. It shattered the foundations of set theory, a branch of mathematics that deals with collections of objects. The paradox was first discovered by Bertrand Russell in 1901 when he asked a seemingly simple question. Does the set of all sets that do not contain themselves contain itself? If it does, then it shouldn't. If it doesn't, then it should. The contradiction is inescapable, and it exposed a major flaw in the logic that mathematicians had been using for decades. At the time, mathematicians believed that sets could be freely defined. If you could describe a group of objects, that group should exist as a set. But Russell's paradox proved that this wasn't always possible. Some sets lead to contradictions just by being defined. This was a huge problem because mathematics depends on logic being consistent. If paradoxes like this were allowed to exist, it meant that the entire system of mathematics could collapse. Russell's discovery sent shockwaves through the mathematical world. To solve the problem, mathematicians had to rebuild set theory from the ground up. The most famous fix was introduced by Ernst Zermelo and Abraham Frankel, who developed a new system called Zermelo-Frankel set theory, ZF. This system avoids self-referential sets, ensuring that paradoxes like Russell's don't arise. Even though modern mathematics has worked around Russell's paradox, the deeper issue of self-reference still haunts many fields. Computer science and programming. Certain types of self-referential problems can cause software to crash or enter infinite loops. Artificial intelligence. Logical paradoxes challenge AI systems that rely on formal logic to process information. Philosophy and logic. The paradox raises fundamental questions about how we define reality, truth, and logical consistency. Final thought. Russell's paradox wasn't just a mathematical glitch. It was a wake-up call. It forced mathematicians, philosophers, and logicians to reconsider the very foundations of logic and knowledge. It also teaches us a deeper lesson. Some questions cannot be answered without breaking reality itself. So the next time you hear someone say, "That's just basic logic," remember that even logic has its limits. And sometimes, those limits are paradoxes waiting to be discovered. The paradox of the ravens. Imagine you're deep in a dense forest, standing still, listening to the distant cawing of a raven. You glance up and spot one perched on a branch, its feathers jet black, its eyes sharp and unblinking. Now, let's say you want to prove a simple statement. All ravens are black. Sounds easy, right? All you have to do is keep finding black ravens, and your theory holds. But then, something strange happens. A philosopher steps in and tells you, actually, finding a green apple also proves that all ravens are black. Wait, what? How can a green apple have anything to do with ravens? Welcome to Hempel's Paradox, also known as the Paradox of the Ravens, a mind-bending puzzle that challenges the very way we think about logic, evidence, and scientific reasoning. And once you understand it, you may never trust proof the same way again. This paradox was introduced by the German philosopher Carl Gustav Hempel in the 1940s, and it's deceptively simple. It starts with something called the principle of confirmation. If a statement is true, then any evidence that supports it should increase our confidence in its truth. So, if the statement is, all ravens are black, then every time we find a black raven, it counts as evidence that supports our claim. No problem so far. But here's where things get weird. Let's rewrite the statement another way. Everything that is not black is not a raven. This is called the logically equivalent form of the original statement. It means the exact same thing, just phrased differently. Now here's the catch. If this version is also true, then finding anything that is not black and not a raven, like a green apple, a blue car, or a white cloud, also counts as evidence that all ravens are black, which means that every time you see a green apple, you're somehow confirming that all ravens are black. And that makes zero sense. Now, something about this logic feels off. Why? Because our intuition tells us that only looking at ravens should tell us about ravens. Why should a random apple have anything to do with birds? But the math behind logic doesn't care about intuition. Technically, every non-black, non-raven object eliminates one more possible counterexample. If we found a white raven, our claim would be false. But every time we see something that is not a raven and also not black, we eliminate one more possibility for white ravens to exist. This means, mathematically, green apples really do support the idea that all ravens are black. But does that actually help us? That's where the paradox comes in. Because even though the logic is sound, it doesn't feel useful. Imagine trying to prove that all swans are white by looking at every chair, rock, and cup in existence. Technically, each of those objects helps confirm your claim. But are you really making progress? No. Only actual swans matter. This exposes a deep flaw in how we think about proof, knowledge, and scientific reasoning. The paradox of the ravens is more than just a logical trick. It challenges the way we do science. Think about how scientists test theories. If we want to prove a law of nature, we look for consistent evidence, just like searching for black ravens. But this paradox raises some disturbing questions. Are we collecting the right kind of evidence? If science allows irrelevant observations like green apples to count as evidence, could we be wasting time on meaningless data? How do we know when we have enough evidence? Just because we haven't found a white raven yet, does that mean they don't exist? What if the one white raven is hiding in a jungle we haven't explored? Are we ever truly proving something, or just failing to disprove it? If we observe 1 million black ravens, we might feel confident that all ravens are black. But it only takes one white raven to destroy the entire theory. This is the essence of scientific skepticism. No matter how much supporting evidence we gather, there's always a possibility that we're wrong. And that's why science is never finished. At the end of the day, the paradox of the ravens isn't just about birds. It's about how we understand reality. If we can be tricked by simple logic into thinking a green apple proves something about ravens, what other flawed beliefs are we holding onto without realizing it? Maybe the real lesson of this paradox is this. Sometimes, what seems like evidence isn't as strong as we think. And if we aren't careful, we might end up believing things that are logically true but completely meaningless. The Ship of Theseus. Are you the same person you were yesterday? Imagine an ancient ship, weathered by time, docked in the harbor. This is the legendary Ship of Theseus. But the ship is old, and over the years, its wooden planks begin to rot. One by one, the planks are replaced. The mast is swapped out. The sails are renewed. Eventually, every single piece of wood, every nail, every rope has been replaced with new materials. And then the question hits you, is this still the same Ship of Theseus? If every single part of the ship has been changed, is it still the original ship, or is it now something entirely different? But before you answer, let's take it one step further. What if someone took all the old, discarded planks and rebuilt another ship from them? Which one is the real Ship of Theseus? This is the Ship of Theseus Paradox, an ancient puzzle that shatters our understanding of identity, change, and what it means to be the same thing over time. And once you realize how deep this paradox goes, you might start questioning everything, including your own existence. The core question is what makes something itself. The paradox was first recorded by the philosopher Plutarch over 2,000 years ago, and since then, it has puzzled some of the greatest minds in history. At its heart, it asks a deceptively simple question. If an object undergoes complete replacement, does it remain the same object? But this question doesn't just apply to ships. Think about yourself. Every cell in your body is constantly being replaced. Your skin sheds, your bones regenerate, your blood replenishes. In fact, scientists estimate that almost every cell in your body is replaced every 7 to 10 years. So if none of your original cells from childhood remain, are you still the same person you were back then? Or have you become someone entirely new? This is where the paradox gets personal. Let's take this paradox beyond philosophy and into real life. Are you the same you over time? The person you were at age 5, at age 15, and now, are they the same person? Or are they different versions of you? If all your memories, thoughts, and even personality traits have changed over time, are you still you? Technology and the future, the human ship of Theseus. Imagine a future where we can replace body parts with artificial enhancements. First, a bionic arm, then a synthetic heart. Eventually, even the brain could be uploaded into a digital system. If every part of you is replaced piece by piece, at what point do you stop being human? The Ship of Theseus paradox isn't just about a ship. It's about the nature of existence itself. Now, what actually defines identity? Philosophers have debated for centuries, but most arguments fall into two camps. Material identity. Identity comes from physical parts. If you replace every single plank of wood, then the ship is no longer the same ship. The original ship was made of different materials, so the new one is just a replica, not the real thing. If you apply this to people, then you are not the same person you were 10 years ago, because your body's materials have completely changed. Continuity identity. Identity comes from history and function. The ship is still the Ship of Theseus, because it has remained the same through time. It doesn't matter if the parts changed. What matters is the continuity of the ship's story. If you apply this to people, then you are still you, even if your body changes, because your memories and consciousness continue. Which one is correct? Well, that's the paradox. At the end of the day, the Ship of Theseus forces us to ask, what does it mean to be you? Is identity something solid or just an illusion of continuity? If we keep changing, then are we ever really the same person from moment to moment? Maybe we are all ships of Theseus, constantly changing, yet somehow still ourselves. So the real question isn't whether we stay the same, but rather, what is it that truly makes us who we are? Schrödinger's cat paradox. Imagine you're in a dimly lit room, staring at a sealed box. Inside the box sits a cat. You don't know if it's alive or dead. But here's the twist. The cat isn't just unknown to you. According to quantum physics, the cat is both alive and dead at the same time. This isn't some horror story. It's one of the most famous paradoxes in science, Schrödinger's cat. A thought experiment so bizarre, it shakes the very foundations of reality. How can something be two things at once? How can a cat exist in a ghostly limbo between life and death? And what does it mean for the nature of reality itself? Buckle up, because this is where logic, physics, and pure mind-bending weirdness collide. In 1935, the physicist Erwin Schrödinger proposed a simple, yet deeply unsettling, scenario to illustrate the strange rules of quantum mechanics. Here's how it works. You take a cat and place it inside a sealed box. Inside the box, there's also a tiny radioactive atom. This atom is unstable and has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that shatters a vial of poison, killing the cat. If the atom doesn't decay, the cat remains perfectly fine. The key detail? Quantum physics says that the atom exists in both states, decayed and not decayed, until we observe it. And if the atom is in both states at once, then so is the cat. Until you open the box and look inside, the cat is both alive and dead at the same time. Wait, what? How can something be two things at once? In the world of everyday logic, this makes no sense. A cat can't be both alive and dead. It has to be one or the other, right? Well, not in quantum mechanics. In the bizarre realm of the subatomic world, particles don't behave like normal objects. They exist in what's called superposition, meaning they can be in multiple states at once. Imagine flipping a coin but never actually catching it, just letting it spin endlessly in the air. In quantum physics, until you observe it, the coin isn't just heads or tails. It's both. The same applies to the atom inside the box. It's in a superposition of decayed and not decayed. And because the fate of the cat is tied to that atom, the cat also exists in superposition, both alive and dead. Only when you open the box does reality choose one outcome. But here's the real question. Does reality only exist when we look at it? Schrödinger's cat is not just a weird science experiment. It's a philosophical bombshell. Because if the cat is both alive and dead until someone looks, then does reality only become real when we observe it? This idea is known as the observer effect, and it suggests that reality isn't set in stone until it is measured or perceived. In fact, real quantum experiments, like the double-slit experiment, show that particles behave as if they decide their state only when they are observed. It's almost as if the universe is saying, you don't get to know the answer until you look, and the act of looking changes the answer. This has led some physicists and philosophers to question, is consciousness directly linked to reality? Do we collapse the universe into existence just by observing it? If no one looks, does anything actually happen? It's a question that goes beyond science, touching on philosophy, reality, and even the nature of existence itself. Schrödinger originally designed this paradox to mock quantum theory, showing how absurd its implications were. But instead of debunking it, his experiment became one of the most famous mysteries of science. So, what does it mean for you? Reality may not be as fixed as we think. The universe might not be a rigid, clockwork machine. Instead, it might exist in multiple possibilities until something forces a decision. Observation changes outcomes. Whether on a quantum scale or in our everyday lives, the mere act of observing can shape what happens next. The world is far weirder than we ever imagined. If something as familiar as a cat can be both alive and dead at the same time, then what other mind-blowing truths are waiting to be discovered? At the end of the day, Schrödinger's cat isn't just about physics. It's about how we understand reality. Maybe life itself is a kind of quantum paradox. Maybe every choice we make splits reality into different possibilities. Different versions of ourselves living out different futures. And maybe, just maybe, until we open the box, we are all in a superposition of infinite possibilities. So, the question is, what reality will you choose? The unexpected hanging paradox. Imagine you're a prisoner, locked away in a dimly lit cell. One day, the warden walks in with a grim announcement. You will be hanged at noon on a weekday. But here's the twist. You won't know the day of your execution until the very moment the hangman arrives at your cell. The execution will be a surprise. Your heart pounds. You replay the words over and over. You won't know the day. But then, a realization dawns on you. If the execution is supposed to be a surprise, maybe it can't happen at all. This is the unexpected hanging paradox, one of the most mind-bending logical dilemmas ever conceived. A prisoner, an executioner, and an impossible contradiction. Let's break it down. The prisoner's logic. Can the hanging even happen? The moment the warden leaves, you start thinking. Hard. If the execution hasn't happened by Thursday, then it must be on Friday, since the warden promised it would be within the week. But wait. If you wake up Friday morning still alive, you'll know with certainty that the execution must be that day. But the warden said it would be a surprise. So the execution can't happen on Friday, because by a process of elimination, you'd see it coming. That means Thursday is the last possible day. But now, if the execution hasn't happened by Wednesday, then Thursday becomes predictable too. And if Thursday is predictable, it can't be Thursday either. This logic continues backward. If the execution hasn't happened by Tuesday, then Wednesday is no longer a surprise. If it hasn't happened by Monday, then Tuesday is no longer a surprise. By this reasoning, the execution can't happen at all, because every possible day becomes predictable in advance. The prisoner, now convinced that the warden has made an impossible claim, relaxes. He smiles. The execution will never come, until one day, the shocking twist. Imagine it's Wednesday. You've spent the past 2 days growing more confident that the execution will never happen. The logic is solid, airtight. The warden's words were a trick, a logical impossibility. Then at exactly noon, the hangman enters your cell. Your stomach drops. Your mind races. This wasn't supposed to happen. You were sure the execution was impossible. But in that moment, standing face to face with the hangman, you are surprised. And just like that, the paradox is complete. Why this works. So, what went wrong? How did the prisoner end up being wrong despite his seemingly flawless logic? The paradox hinges on the way we think about knowledge and prediction. The prisoner assumes that eliminating Friday means he can eliminate Thursday, and that eliminating Thursday means he can eliminate Wednesday, and so on. But this logic only works if he survives each day. Every step of reasoning is based on the idea that he makes it to the next day to keep eliminating options. The moment the execution actually happens, it does surprise him because his logical chain is broken. This paradox plays a trick on our understanding of self-referential logic. The prisoner's reasoning assumes that his own survival keeps proving him right. But the instant the hangman arrives, his entire system collapses. What this paradox teaches us. At first glance, the unexpected hanging paradox seems like just an interesting brain teaser, a clever game of logic gone wrong. But it actually exposes deep flaws in human reasoning, probability, and even philosophy. It challenges our assumptions about knowledge. The prisoner was certain that he had disproven the execution, yet he was still wrong. What other things do we assume are impossible just because our reasoning feels airtight? It shows that certainty is an illusion. The prisoner believed he had logically eliminated every possibility. But reality doesn't always follow our mental models. It's a lesson in expectation versus reality. Just because something seems impossible doesn't mean it actually is. The world often surprises us, even when we think we've figured everything out. Final thought. This paradox taps into a deep philosophical question. Can we ever truly predict what will happen in our lives? We often try to outthink the world, plan for every outcome, and convince ourselves we have certainty. But just like the prisoner in his cell, we forget one thing. Life is full of surprises. And sometimes, the moment we think we have it all figured out, the hangman arrives. The paradox of value. Imagine you're stranded in a scorching desert. The relentless sun beats down on you, and every breath you take feels heavier than the last. Your throat is dry, your body weak. Then, in the distance, you see it, an oasis, a shimmering pool of crystal clear water. At this moment, nothing in the world matters more than that first life-saving sip. Now, shift the scene. You're in an extravagant jewelry store, surrounded by the finest diamonds, brilliant, flawless, each worth a fortune. The air is crisp, the ambience luxurious. And yet, despite their beauty, these diamonds cannot quench thirst, cannot sustain life, cannot do what a simple glass of water does effortlessly. And yet, they are astronomically more expensive. This is the paradox of value, also known as the diamond water paradox, a perplexing contradiction that challenges our understanding of worth. If water is essential for survival, and diamonds are purely ornamental, why is it that society values diamonds more than water? Let's step deeper into this enigma, peeling back the layers of logic, perception, and economic theory to understand why our world functions the way it does. Water is the very essence of life. Without it, civilizations crumble. Without it, the human body cannot survive. And yet, in most places, water is cheap, flowing freely from taps, rivers, and reservoirs. On the other hand, diamonds, which serve no fundamental survival purpose, are treasured, hoarded, and sold for millions. It seems backward. Shouldn't the things we need most be the most valuable? Shouldn't the difference between life and death cost more than a shiny rock? At first glance, this paradox defies all logic. But as we dig deeper, the truth becomes clear. The answer to this mystery lies in two powerful economic principles: scarcity and marginal utility. Scarcity, water, despite being necessary for survival, is generally abundant. Most people have access to it daily, whether through nature or infrastructure. Because of this availability, water holds little market value. Diamonds, however, are rare. Their scarcity makes them desirable, driving their price to extraordinary heights. Marginal utility. This is where the paradox really takes shape. Marginal utility refers to the additional satisfaction or usefulness gained from consuming one more unit of something. Think about it this way. The first glass of water in the desert is invaluable, life-saving, even. But what about the second, the third, the 10th? At some point, the next glass of water loses its urgency. In contrast, diamonds, being rare and symbolic of wealth, retain high perceived value. Water may be crucial for survival, but because it's widely available and each additional unit isn't as urgently needed, its price remains low. Diamonds, on the other hand, are scarce and their demand is artificially maintained through limited supply, making them exponentially more valuable in the marketplace. A story of perception, the illusion of worth. Imagine you walk into a luxury car showroom. The sleek design, the gleaming finish, the prestige. All these factors make the car seem worth its hefty price tag. Yet a simple, reliable sedan could take you to the same destinations. The difference? Perception. Diamonds are not just rare. They are marketed as symbols of love, success, and exclusivity. The allure of owning something few can afford is a psychological trigger. The same logic applies to designer brands, luxury watches, and high-end technology. These items may not always provide more function, but their perceived status makes them irresistible to consumers. Water, despite its immeasurable importance, is not marketed as a luxury. It's not rare. It's not exclusive. And so, its price remains deceptively low, despite its true value being immeasurable. Now, let's flip the script. What if suddenly, fresh drinking water became the rarest resource on Earth? Imagine a future where clean water is as difficult to obtain as diamonds, locked away in vaults, rationed, controlled by the wealthiest elites. Suddenly, water would no longer be cheap. It would become the most sought-after commodity, surpassing even gold and diamonds in value. We see glimpses of this reality today. In drought-stricken regions, water is more valuable than oil. In some areas, wars have been fought over access to clean water. The paradox isn't that water is inherently less valuable. It's that we take its abundance for granted. The diamond water paradox isn't just about two objects. It's a reflection of how markets assign value. Essential goods like air and water remain inexpensive because they are widespread. Luxuries become expensive because their scarcity fuels desire. But here's the deeper lesson. True value is not just about price tags. It's about necessity, impact, and availability. While the world may tell us that diamonds are more valuable than water, reality whispers a different truth. In a moment of crisis, when life is on the line, all the diamonds in the world mean nothing compared to a single sip of water. The final thought. This paradox forces us to confront an unsettling reality. We don't always value things based on their real importance. Our choices, our desires, and even our economy are shaped by perception, scarcity, and social conditioning. And so, we must ask ourselves, are we chasing things that truly matter? Or are we being led by illusion? Do we appreciate the essentials in life? Or do we only recognize their worth when they're gone? And in a world where scarcity determines price, what are the things that truly hold immeasurable value? Because at the end of the day, when we strip away the marketing, the luxury, and the illusion, the truth remains. Water is life, diamonds are decoration, and real value is not always what we're told it is. So, tell me, what do you truly value? The paradox of choice. Imagine stepping into a sprawling gourmet market, where every shelf is laden with a dizzying array of choices. The air is rich with enticing aromas, and your eyes dart from one dazzling display to the next. At first, the sheer abundance of options seems like a dream come true, a veritable feast for your senses. But as you wander deeper into the labyrinth of choices, a curious feeling begins to take hold. Instead of excitement, you start to sense a subtle anxiety. This, my friend, is the paradox of choice in action, a counterintuitive phenomenon where more options can lead not to liberation, but to hesitation, dissatisfaction, and even regret. In today's modern world, we are spoiled for choice. From the moment we wake up to the time we go to bed, every aspect of our lives is punctuated by decisions. Which brand of coffee to savor, what style of clothing to wear, which streaming service to binge, or even which career path to follow. It seems as though every product, every service, every experience has been meticulously designed to cater to our unique tastes and desires. Yet, as the shelves overflow with variety, something unexpected happens. The weight of choice can become overwhelming. Imagine standing in front of an endless rack of beautifully packaged cereals. At first glance, each box beckons with vibrant colors and promises of a healthy, delicious start to your day. But as you gaze upon the multitude of options, your mind begins to whirl with possibilities. Which one truly represents the best choice for you? The promise of making the perfect selection morphs into a paralyzing pressure. In that moment, instead of feeling free, you find yourself caught in a web of indecision, where every option seems to carry the potential for regret. The promise of choice is often sold to us as the ultimate freedom. After all, isn't having options a sign of progress, an indicator of our ability to customize our lives to our liking? And yet, the paradox reveals a more nuanced reality. When confronted with too many options, our expectations soar. We begin to imagine that one of those choices must be absolutely perfect, ideal in every conceivable way. But this idealization comes at a price: the fear of making the wrong decision. Consider the feeling you get after making a significant purchase or choosing a restaurant for a special occasion. Even if the choice turns out well, a lingering thought may whisper, what if the other option was even better? This is the trap of regret, where every decision is shadowed by the opportunity cost of the alternatives you didn't select. The more options you have, the greater the chance that you'll wonder later on whether you could have had a better experience if you had chosen differently. In essence, while options can expand your possibilities, they can also narrow your contentment. Let's step into the shoes of someone faced with an endless menu at a restaurant. The menu is a masterpiece of variety, offering every dish from every cuisine imaginable. Initially, the abundance of choices is delightful. However, as you read through the long list, your mind begins to struggle. Each option, with its unique blend of ingredients and flavors, competes for your attention. Soon, the excitement is replaced by a creeping sense of overwhelm. You worry that choosing one dish means missing out on experiencing another equally tantalizing possibility. And with every passing minute, the pressure mounts until making a decision feels almost impossible. This state of decision paralysis, where the fear of making the wrong choice stops you in your tracks, is a hallmark of the paradox of choice. It reminds us that when confronted with too many possibilities, the joy of choice can quickly morph into a burden. The once promised freedom of having options becomes a maze with no clear exit, leaving you both exhausted and dissatisfied. So, what can we do when the vast expanse of choices leaves us feeling lost in a sea of options? One compelling lesson of the paradox of choice is that sometimes less is more. By intentionally narrowing our options, we can reclaim the freedom and satisfaction that choice is meant to provide. This might mean setting boundaries, limiting your options in certain areas of your life, or simply learning to appreciate the choices you do make without constantly dwelling on what might have been. Imagine returning to that gourmet market with a new perspective. Instead of being overwhelmed by every possible option, you now focus on a few carefully chosen selections that truly resonate with your tastes. Each decision becomes a deliberate act, imbued with confidence and contentment. In this simpler approach, you find that the joy of the experience far outweighs the anxiety of endless possibilities. The paradox of choice isn't merely a quirky observation about consumer behavior. It's a profound insight into the human condition. In a world where options abound, our struggle to make satisfying choices is emblematic of the broader challenges we face. Whether it's navigating our careers, relationships, or personal passions, the quest for the perfect option can sometimes lead us astray, trapping us in cycles of doubt and dissatisfaction. Yet, within this paradox lies an invitation to embrace the beauty of simplicity and to find solace in the art of choosing wisely. It is a call to recognize that the abundance of options, while dazzling, need not dictate the quality of our lives. Instead, by cultivating a mindful approach to decision-making, we can transform our experiences from one of overwhelming possibility to one of intentional fulfillment. So, The next time you find yourself standing before a seemingly endless array of options, whether in a bustling store, on an online platform, or at the crossroads of life, take a deep breath and remember, the freedom to choose is a gift, but it is a gift best appreciated when embraced with mindfulness. Allow yourself the luxury of simplicity, and trust that each well-considered choice is a step toward a life filled not with regret, but with satisfaction and clarity. Simpson's Paradox. You are at a grand sports arena on a crisp autumn evening. The stands are packed with eager fans, each cheering for their favorite team. On the field, two rival teams, Team Phoenix and Team Falcon, are locked in an intense competition across two separate tournaments. At first glance, the statistics seem straightforward. In each individual tournament, Team Phoenix outperforms Team Falcon, winning more games and scoring higher. But then, in a twist that defies intuition, when the results from both tournaments are combined, Team Falcon emerges as the overall winner. Welcome to the curious world of Simpson's Paradox, a statistical sleight of hand that challenges our very perception of data. Let's step into the story. In Tournament 1, Team Phoenix might win 90% of its games, while Team Falcon wins 80%. In Tournament 2, the numbers flip. Team Phoenix wins 30% of its games, and Team Falcon, with a remarkable comeback, wins 40%. When you look at the tournament separately, the narrative is clear and consistent. Team Phoenix is superior in Tournament 1, and even though both teams struggle in Tournament 2, Team Falcon edges ahead. However, when you pull the data from both tournaments, something unexpected happens. The combined win rate for Team Falcon turns out higher than that of Team Phoenix. How can this be? The answer lies hidden in the sizes of the tournaments, the number of games played in each tournament. Perhaps Team Phoenix played far more games in the high-win Tournament 1 and fewer in the low-win Tournament 2, whereas Team Falcon's schedule was more balanced or even skewed toward the tournament where it performed relatively better. The overall averages, then, are not simply the average of percentages. They're weighted by the number of games played in each setting. This hidden layer of weighting creates a dramatic reversal when all the data is merged. Simpson's paradox teaches us that the way we slice and dice our data can fundamentally alter the conclusions we draw. Picture the data as pieces of a mosaic. When you examine each piece individually, each tournament, in our example, the picture is clear and logical. But when you assemble the mosaic without paying attention to the size and significance of each piece, the overall image can look entirely different. It's as if two stories are being told simultaneously, and the narrative shifts depending on whether you're zooming in on the details or pulling back to see the bigger picture. At its core, Simpson's paradox occurs when a trend that exists within multiple groups reverses when those groups are combined. In our sports scenario, that variable is the number of games played in each tournament. This subtle, often overlooked detail can tilt the scales dramatically, leading us to a conclusion that contradicts our analysis of the individual groups. Imagine yourself as both a passionate fan and a meticulous statistician. As a fan, you might instinctively believe that if Team Phoenix wins more in each separate tournament, they should unquestionably be the better team overall. Your heart is set on the thrill of clear victories and consistent performance. But as a statistician, you know that reality is rarely so simple. The aggregated data, with its hidden weights and balances, reveals a different story, a reminder that our intuitive grasp of fairness and superiority can be upended by the raw, unyielding nature of numbers. This duality is what makes Simpson's paradox so mesmerizing. It's a vivid demonstration that data, much like life itself, often carries layers of complexity beneath the surface. The paradox invites us to look deeper, to ask why the numbers are telling a different story when combined, and to uncover the hidden factors that drive these counterintuitive results. The implications of Simpson's paradox extend far beyond the sports field. In medicine, for instance, a treatment might appear effective when analyzing separate patient groups, yet the overall data could suggest the opposite. In social sciences, aggregated data might mask disparities between subgroups, leading to policies that fail to address the needs of specific communities. In each case, the paradox challenges us to question our assumptions and to recognize that the way we group and interpret data can have profound real-world consequences. Imagine a policymaker who, upon seeing the aggregated data, believes a certain intervention is working. Yet, when the data is disaggregated, it becomes clear that while the intervention is beneficial for one group, it might be harmful or less effective for another. This realization is both a humbling and empowering call to approach data with nuance and care, an invitation to let curiosity and rigor guide us beyond surface-level conclusions. So next time you come across a set of statistics that seem to tell one story, take a moment to wonder, what might be hidden beneath the surface? Simpson's paradox is not merely a mathematical curiosity. It's a celebration of complexity, a reminder that the universe of data is as rich and layered as the cosmos itself. It encourages us to embrace the unexpected, to look at every angle, and to appreciate that sometimes the truth is woven from threads that only reveal their full pattern when we dare to step back and view the entire tapestry. As you leave the arena, whether it's a literal stadium, a bustling office filled with charts and graphs, or the quiet solitude of your own reflections, carry with you the lesson of Simpson's paradox. Let it remind you that every set of data holds secrets waiting to be uncovered, and that by delving into those details, we not only sharpen our understanding, but also gain a deeper appreciation for the intricate dance between intuition and reality. The Fermi Paradox. Imagine yourself lying on a grassy hill under a canopy of endless stars, a vast, inky ocean punctuated by shimmering islands of light. As you gaze upward, a question, both haunting and exhilarating, stirs in your mind. Where is everybody? This is the very essence of the Fermi Paradox, a cosmic riddle that dares us to question our place in the universe and the silence that surrounds us in a realm so full of potential life. Enrico Fermi, the brilliant physicist behind this paradox, once mused over the apparent contradiction. If the universe is teeming with billions of stars, each potentially hosting planets and, by extension, intelligent life, then why haven't we encountered any signs of alien civilizations? It's as if the cosmos were hosting the grandest party imaginable. Yet when you arrive, you find the room utterly empty. This eerie quietude in the midst of such boundless possibility is what has kept scientists, philosophers, and dreamers captivated for decades. Picture the universe as an immense, bustling city, where every star is like a glowing beacon and every planet a tiny apartment that could harbor life. In this celestial metropolis, the odds seem stacked in favor of abundant, vibrant communities. Yet, as you wander through this cosmic city with your telescope as your guide, you find that the streets are silent. No neon signs, no cosmic billboards broadcasting the existence of extraterrestrial neighbors. This stark absence of evidence forces us to confront the paradox. Despite the high probability that life should have emerged in many corners of the galaxy, our instruments and explorations have yet to pick up a whisper, a signal, or even a fleeting glimpse of another civilization. The silence is deafening, and it beckons us to ask, why are we alone? The Fermi Paradox isn't a single neat answer. It's a tapestry of possibilities, each more intriguing than the last. Rare Earth hypothesis. Perhaps Earth is a cosmic anomaly, a rare jewel in a vast, barren expanse. The conditions that allowed life to flourish here might be so unique that even if planets abound, those capable of nurturing intelligent beings are exceedingly scarce. Imagine the universe as a colossal lottery, where the winning ticket is far rarer than we dared to hope. The Great Filter. One of the most dramatic explanations is the notion of a great filter, a formidable barrier that prevents life from advancing beyond a certain point. This filter could lie in the formation of life itself, the leap from simple organisms to complex beings, or the technological and societal hurdles that accompany civilization. It's as if every civilization must navigate a gauntlet of existential challenges, and only a select few ever make it through unscathed. Self-imposed isolation or disappearance. Consider the possibility that advanced civilizations, having mastered technology and power, choose to remain silent, perhaps out of caution, philosophical restraint, or even fear of the unknown. Alternatively, they might have self-destructed after reaching a peak, their echoes lost to time. In this narrative, the silence is not evidence of absence, but rather a tragic tale of potential gone awry. Imagine the thrill of standing on that hill under the stars, your heart pulsing with the wonder of the unknown. Every glimmer in the sky represents a potential story, a civilization that might have risen, thrived, or faded into oblivion. The Fermi Paradox invites you to participate in this grand mystery, urging you to contemplate the forces that shape life and the destiny of civilizations. It's a paradox that doesn't offer easy answers, but rather opens a dialogue between what we know and what we yearn to understand. The silence we observe isn't a void of meaning. It's a canvas on which we project our hopes, fears, and dreams about the cosmos. Perhaps the absence of detected alien life is not a reflection of emptiness, but a testament to the myriad ways life might choose to evolve, hide, or simply be fleeting in the cosmic timeline. As you lie there, cradled by the gentle hum of the universe, allow the Fermi Paradox to spark your curiosity. It's a call to adventure, a challenge to our intellect and imagination. Every unanswered question is an invitation to explore further, to build better telescopes, to listen more intently, and to imagine more boldly. The paradox reminds us that our quest for knowledge is as much about embracing uncertainty as it is about uncovering concrete truths. It's a journey that spans not only the physical vastness of space, but also the inner expanses of our curiosity and wonder. In the end, the Fermi Paradox stands as a celebration of the unknown, a reminder that the universe, in all its unfathomable grandeur, still holds secrets waiting to be revealed. So, the next time you gaze up at the starry sky, let the silence speak to you. In that quiet, there lies a profound invitation to dream, to question, and to push the boundaries of what we know. Whether one day we receive a cosmic greeting or continue to wonder in silence, the Fermi Paradox endures as one of the most beautiful mysteries of our time, a mystery that compels us to explore the infinite, to search for our cosmic kin, and to celebrate the wonder of being alive in a universe filled with endless possibility. Olbers Paradox. Imagine yourself standing alone on a vast, quiet plain under a cloudless night sky. The darkness stretches out before you like an endless velvet curtain, punctuated only by the gentle twinkle of distant stars. In your heart, you wonder, with an infinite universe brimming with countless stars, why isn't the entire sky ablaze with light? This, my friend, is the mystery at the core of Olbers Paradox. Picture the universe as a magnificent, ancient tapestry woven with billions upon billions of stars. Each star, a radiant beacon of energy and life, should in theory contribute its glow to the cosmic canvas. If the universe were infinite, static, and uniformly filled with these luminous gems, then every line of sight from your vantage point should eventually land on a star. The inevitable conclusion would be a sky as bright as the surface of the sun, a dazzling, overwhelming light that would banish the darkness of night forever. Yet, as you gaze upward, you are met not with brilliance, but with deep, serene darkness. This puzzling contradiction is what Olbers Paradox compels us to explore. Named after the German astronomer Heinrich Olbers, who popularized it in the 19th century, Olbers Paradox challenges our intuitive notions of an infinite universe. The paradox asks a deceptively simple question. If the cosmos is boundless and eternally populated by stars, why doesn't every direction in the sky shine with light? How can it be that, in a universe teeming with incandescent orbs, we are left with such profound darkness? The resolution of Olbers' paradox lies in a series of revelations about the true nature of our universe. Revelations that shake the very foundations of what we once believed about the cosmos. The universe has a beginning. The first key insight is that the universe is not eternal. Modern cosmology tells us that the universe had a beginning, a moment of brilliant genesis known as the Big Bang. Because the universe is only about 13.8 billion years old, light from the most distant stars and galaxies hasn't had enough time to reach us. Think of it as a grand cosmic play that is still unfolding. Some acts of the performance are yet to be witnessed by our eyes. The expanding cosmos. Next, consider the fact that our universe is not static, but is continually expanding. This expansion stretches the very fabric of space, and with it, the light traveling through that space is stretched as well, a phenomenon known as redshift. As light waves stretch, they shift toward the red end of the spectrum, eventually becoming so faint that they slip out of the visible range entirely. In other words, many distant stars and galaxies are quietly receding into obscurity, their light diminished by the relentless expansion of space. The finite lifetime of stars. Another crucial piece of the puzzle is the reality that stars are not eternal. They have lifespans brilliant, but finite periods during which they shine. Many stars that once blazed might have already exhausted their fuel and faded into darkness or exploded in a spectacular supernova, their light no longer contributing to the cosmic glow. The universe's current star population is only a snapshot in a vast cycle of birth, evolution, and eventual demise. As you stand under the cosmic dome, the darkness above is not an absence but a storyteller, whispering secrets of cosmic evolution. It tells you that the universe is dynamic, a place of beginnings and endings, of expansion and transformation. The profound darkness of the night sky is not a void. It is the result of a universe that is both young and ever-changing. Imagine, if you will, a grand library of light, where each star writes a chapter in the cosmic chronicle. But this library is not infinite in the way we once imagined. Its shelves are still being filled, and many volumes remain unwritten. The darkness is simply the space between the illuminated pages, a canvas on which the next chapters of cosmic history will be penned. Olbers' Paradox is much more than a curious riddle about the night sky. It is a window into the very nature of existence. It forces us to re-examine our assumptions about infinity and eternity. It reminds us that even when faced with what seems like an overwhelming abundance, an infinite number of stars, the deeper truths of time, space, and change govern the ultimate outcome. In the realm of cosmology, the paradox serves as a bridge between observation and theory. It challenges us to reconcile the simplicity of an infinite, static universe with the complex, evolving reality revealed by modern science. And in doing so, it has paved the way for revolutionary ideas about the Big Bang, cosmic expansion, and the ultimate fate of the cosmos. So next time you find yourself under a starry night, take a moment to appreciate the mystery overhead. The darkness is not a flaw in the universe, but a testament to its wondrous complexity. It is an invitation to explore, to question, and to marvel at the profound forces that have shaped the cosmos. Let the dark sky remind you that every star you see, and every star you don't, is part of an extraordinary story spanning billions of years. The night is a mosaic of light and shadow, a cosmic dance between the known and the unknown. It speaks to the delicate balance of creation and change, urging you to look beyond the immediate brilliance and to see the deeper beauty in the vast, unfolding mystery of the universe. The Monty Hall Paradox. Imagine yourself stepping onto the dazzling stage of a high-stakes game show, a place where bright lights, roaring applause, and the thrill of possibility fill the air. Before you stand 3 gleaming doors, each hiding a mystery behind its polished facade. One door conceals a gleaming prize, a brand-new car that promises freedom and excitement, while the other 2 hide goats, symbols of humorous disappointment. This, my friend, is the Monty Hall Paradox in all its captivating glory. Picture the scene. The host, Monty Hall himself, exudes charm and mischief. With a wink and a knowing smile, he explains the rules of the game. You are to choose one door, hoping to unlock the path to the coveted car. You make your selection, your mind swirling with dreams of the open road. But just when you think the outcome is sealed, Monty, who knows what lies behind each door, intervenes. With a flourish, he swings open one of the 2 doors you did not choose, revealing a goat in all its humble, bleeding glory. Now, the plot thickens. Monty then offers you a tantalizing proposition. Would you like to switch your choice to the remaining unopened door? In that electrifying moment, you are thrust into a paradox that challenges both intuition and probability. At first blush, the decision seems innocuous. After all, 2 doors remain, and it appears that the odds are now 50-50. Should you stay with your original choice, or should you take a leap of faith and switch to the other door? The answer, however, defies our gut instinct. Statistically speaking, you double your chance of winning the car if you switch. Let's walk through the drama step by step. The initial choice. When you first pick a door, there's a 1 in 3 chance, about 33.33%, that you've chosen the car. Conversely, there's a 2 in 3 chance, roughly 66.67%, that the car lurks behind one of the other 2 doors. Monty's revelation. Monty, ever the cunning orchestrator, always opens a door that hides a goat. His action is not random. It's a deliberate move, informed by his insider knowledge of what lies behind each door. The fork in the road. Now, with 1 door showing a goat and 2 doors left in the game, the critical question emerges. Does switching really boost your odds? Surprisingly, yes, it does. Here's where the magic of probability unveils itself. If your initial choice was indeed the goat, a scenario that happens 2 out of 3 times, Monty's intervention leaves the remaining unopened door concealing the car. In other words, by switching, you capitalize on the higher probability that your first pick was a mistake. Consider it this way. Imagine fate is like a mischievous storyteller. When you choose a door, fate already has a 2 in 3 chance of setting you on a path toward a goat. Monty's reveal doesn't alter these odds. It merely shines a spotlight on what fate has already determined. Thus, by switching, you effectively claim the prize that was more likely destined for you from the start. Let's envision a theatrical performance. You're in the audience of a grand theater, where the plot twists are as unpredictable as life itself. The actor you initially cheer for takes the stage first, but then mid-performance, The director steps in and casts a brilliant understudy who has been waiting in the wings. Now, the understudy, unknown and underestimated, has a 66.67% chance of delivering a show-stopping performance, while the star is more likely to fumble. The wise move: bet on the understudy by switching your allegiance. That's the essence of the Monty Paradox. A dramatic shift in perspective that defies your initial gut feeling and rewards the brave. Imagine the rush of adrenaline as you weigh your options. On one side is the comfort of your first choice, a decision made in the heat of excitement. On the other, the promise of a better outcome if you dare to change course. It's a moment fraught with tension, where the rules of probability challenge the instinct to cling to what feels familiar. This paradox touches us on a personal level. It's not merely a game of chance. It's a reflection of life's many crossroads. Often, we find ourselves at a juncture where the safest or most obvious choice isn't necessarily the best one. The Monty Paradox reminds us to question our assumptions, to look beyond the surface, and to trust in the sometimes counterintuitive logic of probability. The allure of the Monty Paradox extends far beyond a television set. It is a microcosm of the choices we make every day, where information is incomplete and outcomes are uncertain. Just as Monty's reveal forces you to reconsider your initial choice, life often presents us with unexpected twists that compel us to adapt and pivot. In the realm of business, for example, initial strategies might seem promising, only to be upended by unforeseen circumstances. The savvy decision-maker, like the informed contestant who chooses to switch, embraces change and leverages new insights to secure success. In relationships, too, we sometimes must decide whether to stick with familiar patterns or to embrace transformative change, even when it feels risky. Peel back the layers of theatrics, and you'll find that the Monty Paradox is rooted in simple yet profound mathematical principles. By analyzing the situation through the lens of probability theory, we uncover that the act of switching taps into the underlying odds, shifting a 1 in 3 chance into a robust 2 in 3 probability of success. This elegant solution, though seemingly paradoxical at first, illustrates the power of mathematical reasoning to illuminate the hidden patterns that govern our decisions. As the final bell rings and the stage lights dim, you're left with more than just the thrill of a game show moment. You're carrying with you a deeper understanding of probability, risk, and the value of challenging intuition. The Monty Paradox is a celebration of the unexpected. It's a reminder that sometimes the best strategy is to let go of our initial instincts and embrace the possibilities that lie just beyond the surface. So, the next time you find yourself facing a choice, whether on a game show stage or in the everyday twists of life, remember Monty Hall's challenge. Trust in the unseen hand of probability. Dare to switch your course, and be open to the counterintuitive paths that lead to success. In that brave act of changing your mind, you might just unlock a world of opportunity, much like discovering a shining car behind a door you never expected to open. In the end, the Monty Paradox isn't just a puzzle. It's an invitation to explore the intricate dance between chance and choice, a reminder that life's surprises often come to those who are willing to take a chance and change direction. Embrace the thrill, relish the uncertainty, and let the paradox inspire you to see that sometimes the most rewarding victories are found by daring to step into the unknown. The Friendship Paradox. You're at a bustling party, the kind where laughter echoes, glasses clink, and every conversation feels like a spark of connection. You look around and suddenly, a curious thought pricks at the back of your mind. Why is it that, no matter how hard I try, it seems my friends are always at the center of a larger, more vibrant network? Your heart skips a beat. not out of insecurity, but out of sheer wonder, because you're about to step into the intriguing realm of the friendship paradox. At first glance, it might sound counterintuitive. You'd expect that in the grand tapestry of social relationships, your circle of friends would mirror your own connections. But here's the twist. Statistically speaking, on average, your friends have more friends than you do. This isn't a personal failing or a comment on your own popularity. It's a fascinating quirk of how social networks work. Picture your social network as a sprawling, dynamic web, with each person represented as a glowing node and every friendship as a luminous strand connecting these nodes. Some nodes shine brighter, connected to many others, while some glow more modestly with just a few links. Now, when you casually wander through this network, imagine you're taking a stroll along the threads. You're far more likely to bump into those dazzling, well-connected nodes. Why? Because they simply appear more often in the tapestry of friendships. It's as if the universe is whispering, look closer at those who shine the brightest. They are the ones who make the network pulse with life. And indeed, if you randomly pick a friend from your list, chances are that friend is one of these bright, magnetic personalities who naturally gather more connections. Let's set up a dramatic scenario to truly grasp the paradox. Imagine a small town where every resident has a unique social footprint. Here's a snapshot. Alice radiates charm with 6 friends. Bob is sociable with 4 friends. Carol maintains 2 close connections. Dave has a modest bond with just 1 friend. If you were to calculate the average number of friends per person in this quaint town, you'd add up all their connections and divide by the number of residents. Now, here's where the plot thickens. Instead of randomly selecting a townsperson, you decide to wander through the town by following friendship ties. Because Alice is so well connected, her name pops up repeatedly as people mention their friends. In this friendship-led tour, you're more likely to bump into someone like Alice who, by her very nature, appears in many friend lists. The more connected you are, the more often you're encountered on someone else's journey through the network. Now, let's bring this to life with a more visceral scenario, one that might feel like a scene out of an emotional thriller. Imagine you're standing at the edge of a swirling social current, the atmosphere charged with both excitement and mystery. Every connection you make is a thread in a vast, interwoven tapestry. As you glance over at your friends, a mix of admiration and bewilderment stirs within you. How can it be that those you hold dear seem to command such a vast circle of acquaintances, while you feel, in comparison, a bit more modestly connected? Your mind races, and you start to see that this isn't a personal indictment. Rather, it's a statistical inevitability. The paradox isn't a measure of your worth. It's an echo of the natural structure of social networks. Think of it like this. If popularity were a river, the strongest currents would naturally carry more water. Those with many connections simply create larger, more noticeable ripples in the social pond. The secret behind the friendship paradox is a phenomenon known as sampling bias. In the grand experiment of life, when you're selecting friends at random, you're unwittingly favoring those who are already popular. It's like fishing in a pond where the bigger fish swim in schools. They're simply more likely to be caught in your net. Because popular individuals appear in so many friend lists, they skew the average, making it seem like everyone's out there is living in the fast lane of social connectivity. This paradox isn't confined to abstract theory. It has real-world implications that ripple through various domains of life. Consider how it influences our perception of social media. Scroll through your feed, and you might notice that everyone seems to be living a life filled with connections and interactions. That ever-present feeling of missing out? It's partly a product of this statistical quirk. Social platforms, by their very design, highlight those with massive networks, making it seem like every friend is a superstar of connectivity. But there's a silver lining. By understanding the friendship paradox, you can reframe your perspective. Instead of feeling inadequate, realize that your experience is part of a larger, fascinating pattern, a natural outcome of the way our social world is organized. This insight can empower you, whether you're a sociologist studying human behavior, a marketer targeting influencers, or simply someone trying to navigate the often perplexing landscape of friendship. The beauty of the friendship paradox lies in its ability to unveil the hidden dynamics of our social lives. It's not just an academic curiosity. It's a gateway to understanding how information spreads, how communities form, and even how epidemics or viral trends can cascade through society. In the realm of public health, for example, recognizing that your average friend might be more socially connected can lead to smarter strategies in vaccination campaigns, where targeting the most connected individuals could save countless lives. In marketing, the paradox is a clarion call to focus on influencers, the well-connected individuals who naturally amplify messages. And in the realm of social psychology, it challenges us to reconsider our notions of self-worth and popularity. Instead of measuring our value by the number of connections we have, we begin to appreciate the intricate, often unseen forces that shape our social networks. So next time you find yourself wondering why your friends always seem to have a larger circle than you, remember, you're witnessing a fundamental property of social networks. The friendship paradox is not a critique. It's a celebration of the diversity and complexity of human relationships. It reminds us that in the grand, interconnected dance of life, some will naturally shine a bit brighter. And that's simply how the tapestry is woven. Stand tall, knowing that your place in the network is unique and valuable. Embrace the paradox as a testament to the rich, interconnected fabric of human society. Every friendship, every connection is a thread in this ever-evolving masterpiece, and you're an integral part of its intricate design. So, the next time you catch yourself comparing your social life to those dazzling, well-connected friends, take a moment to appreciate the logic behind the magic. It's not about being less or more popular. It's about understanding that every network has its own rhythm, and every person plays a part in its grand symphony. If you enjoyed this journey into the mysteries of logic and science, make sure to hit the subscribe button. It helps the channel grow and brings you more thought-provoking content to fall asleep to. And if you're still awake, let me know what you think in the comments. Thanks for watching, and I'll see you in the next one.